Alright, let's move into a little bit more of ocean physics, and let's take a look at how knowledge of those physical properties that we just talked about, the technology for measuring, how does that help us understand the world ocean? Well, first we need some definitions, some basic definitions, and these definitions again are not the kind of thing that I'm going to expect you to get too involved in, alright? This isn't an advanced course in physics. But for some of you that have had this kind of thing, or some of you that might be going on to have a career in physics, or those of you that just might be interested in this topic, it's always good to have a specific definition for a particular word that's in use all the time. The word energy is something that we use a lot, and in the sort of official scientific way, the word energy actually means... Go ahead. I'm going to come back to this. Okay, let's now look at a little bit more complicated things like the physics of the ocean itself. And let's ask, how does knowledge of the physical properties of water help us understand the world ocean? So what we want to try to do in this section is take some of the molecular properties of water. We looked at some of the chemical properties of water in the last chapter, but let's look at some of the physical properties of water itself and see how water combined on a global scale, how those properties of the molecules work on a global basis. And I think you'll be astounded. First, let's define some words. Energy is the capacity to do work or produce a change in some system. Now, this is probably a much more complicated definition than you need to know, but for sort of specificity and in the interest of being as accurate as possible in what we're describing, it's good to know that. Some of you may be going into physics, or you may have an interest in physics. So here's a website you might want to go to get kind of a better idea of what this word energy is. We use that word a lot these days, and it's kind of nebulous or vague what it means, and that's fine. As long as you have some sort of intuitive understanding about different kinds of energy, then you'll be fine. So let's not get too tripped up on what energy is itself. Okay, different kinds of energy. My favorite energy is solar energy, the radiant energy from the sun, the electromagnetic energy that comes from the sun. And we'll take a look at that in a little bit more detail in just a few minutes. We also have kinetic energy, which I already defined. It's the energy of motion. So the moving molecules in winds or motions of water in a glass. Thermal energy or heat energy is the internal energy that's contained within those molecules. So it's not the motion, the energy of motion, as we talked about. Thermal energy is just the energy in itself. And heat's one of those words, again, that gets butchered really in its scientific sense. Heat doesn't exist if two temperatures of two systems are the same. Heat is really only exists, and heat is exchanged when two systems have different temperatures. Now I know that seems complicated, but just bear with me for a minute, okay? Chemical energy is the energy within the chemical bonds of substances. So when you burn a piece of wood or when you burn a candle, you are converting the molecules of the wood or the molecules of the wax into a different kind of energy. In fact, you're converting into heat energy, and you're releasing the energy that was stored within the molecules of those particular substances or those materials. Potential energy is just Humpty Dumpty energy. It's related to the position of an object or a molecule, specifically with relation to gravity, for example. And if you really want to get more into this, you can go to Kids Facts or go to the Energy Information Department Administration at the Department of Energy of the government, and there's lots of great things in there that will help you better understand this. And I highly recommend that you check out that website, because it's a good place just to get a kind of a different feeling for, or a different sense of what these different kinds of energy are, because we're going to talk about radiant energy or solar energy. We're going to talk about kinetic energy, particularly when we talk about waves. We're going to talk about chemical energy when we talk about photosynthesis. So all these things are really important to our understanding of how the ocean works. All right, we already talked about some of water's unusual properties, and as it turns out, water is really an amazing substance in its molecular properties. In fact, there's people studying water today. You'd think we might know everything there is to know about it. Not a chance. Here's an interesting fact. Water theoretically should boil at minus 60 degrees. If water boiled at minus 60 degrees, what would that mean for our planet? That would mean that most water on our planet would be vapor. We would just be like Venus, probably. Instead, it boils at 100 degrees centigrade. Why? Nobody really knows. It has to do with the unusual molecular properties of water itself. And when I say nobody really knows, nobody like me really knows, but I'm sure there's some physicist somewhere that has some idea of why water boils at 100 degrees centigrade instead of minus 60 degrees. Okay? Water, and this is important, has the second highest specific heat, and we're going to talk about what that is in just a few minutes. Water can absorb heat and release heat, and it can absorb more heat per gram of water than just about anything else. And that means that holding that heat when water moves around on our planet, currents in the ocean, as air moves and as water vapor moves through the atmosphere, it's moving heat around. Water is really a transportation system for heat on our planet. This is really important because this is where heat and heat transport on our planet really play a big part, and water has a central role in that. Here's another really good property of water that most of you are familiar with. Ice floats. So imagine if we lived on a planet where ice didn't float. We'd be playing hockey underwater. We would be very frustrated trying to get the ice cubes out of the glass when we're sitting at Lonely Hearts Bar. It would just kind of not be as much fun if ice didn't float. So why does ice float? Well, we'll talk about that, perhaps. Water also has this ability to bead up, and if you've ever washed your own car or if you've ever spilled water on a table, you will see that it forms beads, and it's that cohesion of water that really lets many different kinds of organisms skim across the top of the water. And we're not going to talk a lot about cohesion. It doesn't concern us too much here, but it's, again, just a good and fun thing to know about. Okay, here's some real kind of high-powered definitions, and this is one you really have to pay some attention to. Specific heat. It's the quantity of heat absorbed or lost by a given amount of a molecule or a set of molecules or an object that results in a temperature change of 1 degree. Okay, what does that mean? That means if I have 1 gram of water and I heat it up by 1 degree, the amount of heat is the specific heat for the water. So it's the heat needed to change 1 unit of something by 1 degree. If you say that repeatedly, I think you'll get it. And I think you can remember that. The specific heat, the amount of heat needed to change the temperature of water by 1 degree. And not all water, but just 1 unit of water, such as a gram of water or a cubic centimeter. As I've already said, water has the second highest specific heat. Only ammonia has a higher specific heat. And by definition, the specific heat of water is 1 calorie per gram. Okay? And the way to think about a gram of water is just a little bit, it's just a cubic centimeter. It's less than maybe even a teaspoon of water. It's 1 milliliter. If you have ever seen a graduated cylinder or even a syringe in millimeters, you will have seen what a millimeter or a gram of water looks like. The specific heat then, or 1 calorie, is the amount of heat that raises that gram of water by 1 degree Celsius. Now let's not confuse this little calorie, see that it has a little c, with the big calorie, the food calorie. They're different kinds of things, and it's confusing, yes, and that's why scientists use joules, 4.18 joules per gram. But it's easier to remember calories, right? So in any case, 1 calorie to raise the temperature of 1 gram of water by 1 degree.